Okay, let's get started. So today we're going to be talking about text and natural language data, which is kind of a cool topic. On to the announcements. The final exam is actually in 1 week. It's in class. Remember, we agreed the last day of class was going to be the exam. So that's in 1 week. So, danger. Yeah, don't forget to come to last lecture. I'll send an email reminder to all the slackers who aren't here. And it's going to cover the same stuff you see in the practice final exams. So it's like SQL, database design, and maybe a little on number representations, not too much. So, but mainly SQL and database design. So that's that. There are a lot of topics I'm covering at the end that are not covered on the final exam. So those are for your, to help you with the projects and for your general information, I guess, and also not covered in homework. And the final project is due in 13 days, so it's after the final exam on that Wednesday. Any questions? That stuff? Yeah. All right. So last time I talked about big data and sort of divided it into two different topics. So the first was distributed hash tables, like NoSQL databases. Yeah, question about the...
On the previous page, number representations,
Yeah.
it's actually saying like what should be represented as a float versus what should be represented.
Yeah. It's not. It's yeah. What's the difference between a float and a integer in terms of like one should use a float, one should use an integer. I guess. Yeah, conversions not so much. Like arithmetic with like binary arithmetic, not so much. I had some homeworks on that before, but we didn't really do that this time around. And
the lecture from Tuesday won't really be covered.
Which one was that?
Well, it's what you talked about.
Oh, last time? Yeah, the big data lecture?
Yeah.
No.
Okay, that's just like for general knowledge.
Yeah, there's not. Right. Even the number representation stuff, I didn't give you homework on, so it's hard to give too much weight to that in exams. And I certainly didn't have any homework on this stuff. But yeah.
Sorry, another question.
Sure.
So even though it's a final, since it's during this class period, it's still only an hour.
Yeah, the length of the exam is going to be the length of the class period,
Okay.
hour and 20 minutes. And it's still going to be cumulative even though it's an hour and 20 minutes, which is going to be a challenge, but I don't know. It is what it is. It'll be fine. Yeah, so it's going to be like probably half SQL queries, so half review of midterm stuff and half database design. And I would especially practice, it's been a while since you've done a lot of queries, so you need to review that stuff. And there are plenty of practice questions to do that review, but also look at the practice exams that have database design questions. Like I think it was like it gave you a picture of a form and asked you to write a schema for it. Like the figure skating one is really hard. I don't know if any of you have looked through that yet, but if you can do the figure skating example, you're in good shape. So keep an eye out for that. Yeah, question? Our homework answer is going to be posted. Yeah. Do you know? I haven't. How many are there? Any of them up yet? Only 1, 2, and 3 are up there. Okay. Yeah, I'll post the other ones. Yeah. If you don't see them tonight, then send me a reminder, please, and I'll definitely post them. Okay. Anyone else? All right. So we'll move on. Last time talked about big data again. NoSQL databases are these multi-computer databases, and we talked about hash functions because that's the fundamental like building block or technology behind distributed databases. This is where you take a element of data, a sequence of bits, and compute a function on it that's sort of not random. It's deterministic in the sense that it's a prescribed set of steps, but it operates in a complex way so that it's kind of unpredictable unless you run it to see what the answer is. Anyway, so it kind of returns a random but deterministic value from an input. And this allows, and we use that output, that hash of the keys, so like the data we want to store, to determine where to store it. And particularly, we can use that to determine which of several computers stores a given data. So if we're looking for all the information about customer John, we could take the name John, hash it, and look at, for example, the last 2 digits of the hash, like divide it by the number of computers or whatever, and that will tell you exactly which of the computers you need to look at to get the information about that person. That's just a very simple overview. And that's advantageous because it allows many analyzing programs at once to access the data that's distributed across the system without having to go to a directory that says where everything is. And so there's no central bottleneck. There's just this function that each of the clients can use to, on its own, determine where to look for data. Okay, so hashing eliminates the need for a central directory, and that allows scalability. Right, so big data analyses involve data sets that can't live on one computer. They're too big for one computer. They can be on a NoSQL distributed database or a distributed file system, which is kind of the same idea. But those kinds of databases don't give you the full power of SQL. You can't really have multiple tables and do joins. You can't index in multiple columns because of the very simple nature of the system, the way that you can only find data according to one of its attributes of one primary key. And also, joins are impractical because you'd have to transfer a lot of data between all these different storage nodes, and that it's not possible to transfer like most of the data on the system throughout the system just to answer a query. The second topic we covered in big data was a particular distributed computing platform called Hadoop, which uses Mapreduce. And so this is a way to, Hadoop is a type of computer cluster that stores data in a distributed way. So similar to it tends to use the Hadoop file system to distribute data. But more importantly, there's a programming model called Mapreduce, where you write your analysis as a sequence as a combination of maps and reduces that somehow compute your result. And so the map function takes the input and produces a bunch of intermediates, and then the reduce takes the intermediates and produces an output somehow. And so we gave like 1 or 2 examples of how that works. But the challenge in using Hadoop is figuring out how to express your analysis in terms of maps and reduce. Just like with using SQL, you have to figure out how to express your analysis in terms of the SQL language. But I think SQL is simpler than Hadoop, and this involves like writing code in a language like Java instead of writing SQL. Okay. And the key takeaway I think for you all is that you should stop and think before using big data tools, because the medium data tools, as I call them, the SQL databases, are actually quite scalable, can handle huge amounts of data. And it's very rare that you have like the petabytes of data that really justify using something like Hadoop or a NoSQL database. Okay. All right, so today's topic, again, another random new topic, but an important one, is about natural language data. So normally when we think about data, we think about numbers, dates, maybe names, like very simple things that are easy to store, easy to reason about, easy to compare. We can ask simple questions about them, like what is the total revenue of orders? That's a numeric question that has a clear numeric answer. But a lot of the so-called data these days is not just numeric, but it's like text. For example, we looked at the Yelp database. We have that Yelp database on MySQL that you did queries on. All those reviews are it's quite a useful data set, but doing an analysis on them, as we found, is kind of difficult. You can count up how many reviews there are. There are stars associated with the reviews. So there's a numeric component to a lot of those reviews that's easy to analyze. But the text itself is hard to get much meaning out of, how to get much use out of. And we'll talk a little bit about how you can do analysis of text today, but we don't have enough time to cover the most advanced topics or the most advanced techniques. But I hope that this gives you a little bit of a flavor of how text analysis systems work. But to start this discussion, I want to define natural language. So When you hear about natural language processing in computer science and in data science, it means, so a natural language is a language that evolved naturally, meaning it wasn't invented. Like, has anyone heard of Esperanto? Is a language that like some linguists decided like all these human languages are kind of like they have their problems. Let's invent a new language and like here's what it is. Here are all the words. Here's how you conjugate them. And somehow it's a more beautiful language than the natural languages we have. But it's those are artificial languages. Those are formal languages. And another example of a formal language is like SQL or Python, R. Those are languages that are defined by a strict set of rules, and someone decided how to define them, and it's easy to interpret those languages because they have strict rules, right? So a computer can interpret SQL or Python and run it, and two different computers will interpret it in the same way because of the formal rules of the language. Natural languages are not like that, okay? Because there are no strict rules for how they're defined. So written English, spoken English, pick your favorite language, human language. Those are all natural languages because they don't have strict rules, right? And they're difficult for machines to deal with because, like I said, there are no clear rules for the semantics. Semantics is just the term we use in computer science to indicate the meaning of something, of a language, of a phrase. So natural language processing is sort of it's within the realm of artificial intelligence. It's a difficult artificial intelligence problem. And so a lot of like researchers at Northwestern and elsewhere are working on ways to deal with natural language. And some of the popular consumer systems of the day, like Siri and Alexa and Google Search, have natural language components built into them, and those are constantly evolving and getting better. And we'll talk a little bit about some of the building blocks and how those analyses start, but we're not going to talk about like the machine learning and the details of state-of-the-art systems. But hopefully, this will give you a little bit of a sense of how some of that analysis can even be done. So, if we have natural language data like these Yelp reviews. Just looking at them, you can see that if we just gave you like R or Python and asked you to do an analysis to figure out what was being said here, it would be hard to begin. Like there'd only be a few things you could do. So because it's not clear how you would. It's hard to define rules, or in other words, code that figures out what is actually being said here, right? I love this fourth review. Great brisket sandwich as claimed. Weird that it's a gas station / hipster barbecue lunch spot / Hallmark store car wash. These are just the first 5 reviews I found on the Yelp database. I did not cherry pick these. Okay, but so the first technique I'm going to introduce here is called is for pattern matching, which is maybe the simplest kind of analysis you would think of for dealing with text. We've already seen like for pattern matching. So if you have some text, and for example, you want to pick out all the reviews that mention pizza, and I think we had a homework question that asked you to do this, you can just compare the text to a pattern, like this percent pizza percent allows the percent to match anything, and then it requires there to be PIZZA in sequence, and after that there can be anything. So like these reviews would match. That might be useful. Picking out words helps you to do filtering, and there are only a few types of questions you can answer with such simple filtering. So we're going to spend a little bit of this lecture talking about a more advanced type of pattern matching technique called regular expressions. And in SQL, there's a regexp keyword for using regular expressions. So, for example, in a where clause, you can say where column regexp pattern. Instead of saying like, And then the pattern you write here can be a lot more complex than just those things with the percent signs. Okay, so whereas like allowed you to use percent size to represent a sequence of unknown characters and underscore to represent a single unknown character, regular expressions are much more powerful, and they can be more specific and more flexible. You can have subpatterns repeat. You can have different choices can be where any one of them can be used, and so on. Okay, and so regular expressions are used in all these, in every major database system, but also in a lot of other computing systems you'll find. So this is a general tool for programming across a lot of different systems, because it was invented a while ago, and pattern matching is a common problem, and everyone kind of decided to use the same system. Most systems have decided to use this particular type of pattern for advanced pattern matching. Okay, and there's some command line tools that do this, and we'll see how that works. So we're going to start off with some simple examples and build it out from there. So you can actually just write out some text, and that's a pattern. So when we look at regular expressions, they're either going to match or not match. So they'll return true if the pattern is present in the text, otherwise not. And the first thing to notice is that they're case sensitive, meaning that capital and lowercase are different characters. So if the regular expression barf, B-A-R-F, matches barf, barfly, I am barfed on my journey and I barfed at McDonald's, all these texts have B-A-R-F in them, and therefore they match. So the pattern doesn't require, it specifies what's there. It doesn't have to specify everything that's there. Okay, so there can be other stuff outside of it. It doesn't match these other options because either there's like a capital letter where the pattern requires lowercase, or only part of it is there, like this bar finally closed. There's a space here between the R and the F. And I enjoyed my meal at McDonald's. Yeah, so, and this one here is missing the B. Okay, so it's pretty clear, right? So this is a simple regular expression. You can use, the point is you can use regular like letters, characters in your regular expression to match things that you want to find. There's more to it than just that, of course, but that's the starting point. All right, so the syntax for regular expressions is kind of complicated, and it can be it can take some trial and error to get right. So so when you're using them, you need to have a way to test them, and you can do that in SQLite. For example, if you do a select statement where you have some string that's your test string, and you want to see whether it matches some pattern, you can say select. You can say select and then put in the regular expression test that you want to do. So this is some test, regex, some pattern. It'll return 1 if it matches, otherwise 0. You can also, on the command line, like on Mac, you can print out some text and then pipe it through grep. Grep is a command line tool. It stands for General Regular Expression Parsers. And it will print out the lines that match the pattern, and it will not print out the lines that do not match the pattern. And I like to, there's a little parameter that colorizes the matches, which is cool, which I like to use. I'll show how that's used in a second. And there's also something similar on Windows called find string or find str on the command prompt. So for example, on Mac, if I have a, so I have this file, Nicar. This is a list of emails that were in my inbox from some mailing list. It's like a really long file. If I want to search these emails for, let's say the word collusion, I can grep with the pattern, and I can give it the file like that, and it'll print out. There's no collusion in my email, okay? So no collusion. Remember that, no collusion. Otherwise, other more common words like email, if I print it out, if I grep for email, this is the command I wrote, grep email nicarl.text. It prints out actually a lot of lines. There happen to be 103 lines that were printed out. And you see that these are each one of these lines has email in it. You can see that with the color always thing. You see in Reddit showing the matches, and what's maybe a little confusing is that some of these lines in the file are larger than a line on my terminal, so they're wrapping around. So this is showing 2 lines actually, but they're just really long lines. And here are other lines that had the word email in them. Yeah. Anyway. So that's for experimenting with regular expressions. But so far we haven't really talked about the syntax and what we can do with regular expressions. So let's try to get into that. There's special characters that you can put in the regular expressions to do some interesting things. And one of those things you can do is tell the pattern. You can represent the beginning of the line and the end of the line, or the beginning of the text and the end of the text with the caret symbol and the $ symbol. So caret means beginning, $ means end. Why, I don't know, but you can just remember that. So like caret hello is a pattern that matches hello when it appears at the beginning, but not hello when it doesn't appear at the beginning. Because in other words, this pattern is saying that the pattern we're looking for is that there's the beginning of the line, and then there's the word, the capital H, and there's an E. So this text big hello does not match this pattern because what's before the H is a space, not the beginning of the line, right? And similarly with the end of the line, you can, if you match world $, that will match hello world, but does not match world cup, because in the world cup text, the $ is preceded by C, not by D. So you can surround your pattern with both caret and $ if you want to precisely match a particular. If you're specifying a pattern that matches the entire line or the entire text, and you don't want to just pick out things where it's the pattern's inside, but there's other stuff to the left and right of it. Okay. And so one of the most powerful features in regular expressions is the ability to match sets of characters so that you can use different variations of spellings and whatnot. So that's what these square brackets are for. So inside square brackets, you can have many different characters, and any one of them can be found. Another thing is that the period matches any one character, which is similar to the underscore. So M period P matches map, mop, and mope. Again, mope matches because I didn't have a $ at the end, requiring it to be at the end. But it does not match. So dimple has M and then P immediately after it. That doesn't match because period requires there to be a character there. And mousetrap has 7 characters or 8 characters in between the M and the P. And obviously that does not match the pattern because this pattern specifies there's exactly 1 character between M and P. Okay. So these regular expressions are going to be ways of specifying patterns of text to hopefully let you find the text data that is relevant for you, whatever that happens to be in your particular analysis. Pattern matching, of course, cannot solve every problem, but it's useful for some problems. Okay. So these square braces, like I said, specify a set of characters. So like square brace A, capital A, closed square brace specifies either lowercase or uppercase a. So that's useful if you want to find a word, but you're not sure whether it's going to be capitalized or lowercase. You want to match both of them. So an example of that. So let's look at another file here. So I have this file, Pride and Prejudice.txt is the novel Pride and Prejudice from Project Gutenberg. So if I want to search for a name like Bennett, I can run grep. So the pattern here is I can just write a simple pattern without any special characters. Sorry, there's a certain version of less that lets me. Yeah, I forgot to put in the name of the file. Okay, so this is searching for all the lines that have the word Bennett, capital B-E-N-N-E-T-T. Those are names, so I would always expect them to be capitalized. I could search for a variation of that has a lowercase b, and I probably wouldn't find anything. Indeed, I don't find anything. But if I'm searching for a word that's not a proper name, sometimes it's capitalized, sometimes it's not, like the, for example. So the appears many times, but the way that I specified it, just THE, doesn't allow it to appear capitalized. If I wanted to allow it to be capitalized, then I have to change the pattern to give two different options for that first character, either lowercase t or capital T. So I change this pattern here. And now it'll match. So for example, on the first line, you see the Project Gutenberg ebook that has capital T, and that is matched. And like in the middle here, the business of her life, that's capital T, that's included. Yeah. But if I was really looking for the word the, this is not a great pattern because why? Yeah, other words like other, for example, O-T-H-E-R, or father, right? So this is not the word the, it's father. So this pattern I have so far, it allows for capitalization, but it doesn't necessarily pick out, it doesn't require that sequence is isolated from other words, right? So let's use some of the syntax to try to fix that problem. So one thing we can do is we can specify different characters, a variety of different characters that can appear. We can also specify a range of characters by putting them between hyphens. So A hyphen Z allows any of the characters between A and Z in the ASCII sequence or the UTF-8 sequence. You can say caret and then a set inside of square braces to specify a character other than what's listed. And you can have multiple ranges and so on. So if I want to pick out the words that are isolated, I need a pattern that will force that to happen. So basically, I need to specify that before and after the THE, there's not another letter, for example, right? So I can add to this pattern something before it. If I want it to be not a letter, I could say caret A through Z and capital A through Z, like that. And at the end, I can do the same thing. So now I have a much longer pattern that says that first I have to have a character that's not some lowercase letter or an uppercase letter. Then I have either a lowercase t or a capital T. Then I have lowercase h, then lowercase e. Then I have something that's not a letter. And now it looks like I have the right pattern. Right? Seems pretty good. Does this pattern allow punctuation, like a the at the end of the sentence? Although we wouldn't really expect the to be at the end of the sentence. Yes.
So like, how do you say like not A to Z and A to Z? Do you need to use like a bracket? We can just say them together.
You see how I wrote this here? So this caret here specifies that this set I'm defining here, I need to match something that's not in that set. And the set is defined in terms of two ranges, lowercase a through z and then capital A through z. Yeah, these sets can be combined. So here's another example of a set of letters that includes, in addition to the lowercase the letters, it includes the characters 0, 1, and 3, just kind of arbitrarily. You can negate a set of specific letters, like here, not capital C, not capital D, not capital A.
It was confusing at first, or last time was caret for starting, so I thought it was start at A.
Yeah, so caret has two different meanings, which is confusing. In the previous slide, I said that caret represents the beginning of the text, which is true, except when it's inside square braces and it's the first thing that appears inside that square brace, it takes on a different meaning. And then also you might want to literally look for the character caret, in which case you have to put a backslash in front of it to escape it. So that's why it's hard to just write complex regular expressions and have them work the first time. It's helpful to experiment with them, do some trial and error, just like with SQL queries, but even worse because the syntax is even harder to read because of these weird, because of the fact that you have characters that take different meaning in different places, and sometimes you want to look for these characters. Like, for example, if you want to include the hyphen character in a set, you can't just write hyphen because hyphen has special meaning inside the square braces. You have to write slash hyphen. And then if you want to include a backslash, you have to write backslash backslash. Because otherwise they would interpret the backslash to mean that you're escaping the thing that comes next. So these are all headaches. So some examples of regular expressions using the building blocks we have so far. Caret, square brace, capital D, lowercase d, close square brace, database. This is looking for the word database either with lowercase or uppercase d, but it has to be at the beginning of the line. That's what this caret means here. So it matches these expressions, but does not match my space database or just data, because data doesn't have the characters at the end that it requires. Okay, and here's another one that has a constant letter and then a set and then another set. So those sets are specifying different possibilities for letters, and any one of them can be chosen for the middle letter and for the third letter. But again, this is just specifying a pattern of 3 characters that can have some variations, but those 3 letters can appear anywhere, like abracadabra matches. There wasn't like a caret or a dollar sign that said that this had to be the only element in the string, but it doesn't match these other ones because, like, for example, clad has an L, the L is not in the pattern, and CB, this capital B doesn't match anything in this pattern. So another pretty simple pattern here is another three-letter pattern, but this 3-letter pattern starts with either capital or lowercase c. There can be anything you want in between. Remember, that's what the period means, any character. And then after that, it has to be something not in this set, A, E, I, O, U, not a vowel. So it's a 3-letter sequence, starts with C, then some letter, and then the third one is not a vowel. It matches all of these, does not match these ones. Okay. All right, so the big important building block for regular expressions is expressing ways to repeat patterns. And star is the simplest way to do that. Star lets the previous thing repeat any number of times, including 0 times. So if you have a pattern and you put star after it, then that allows that thing to repeat or not appear at all. So dot star, for example, matches anything. So that's kind of equivalent to the % sign, because the dot means any one character, and the star means any number of times, including 0 numbers of times possibly. So dot star is commonly used in regular expressions. Instead of the star, you can have plus if you want to repeat something, but you want it to definitely appear at least once. And question mark makes the previous thing optional. It can appear 0 or 1 times. And a generalization of all these, except for star, is this curly brace n comma m lets the previous thing repeat between n and m times. So that's ways to specify repetitions. So, for example, if we want to check for repeating characters in the same text, we can specify a pattern. Like if we want to look for if we say O plus, that looks for cases where the word O is repeated. Why didn't that work? Maybe like this. Looks like a plus isn't working in this in grep, but star allows it to repeat 0. Let's say maybe this will work. With this pattern, I'm trying to say that O can appear once or twice. Yeah, and for some reason that's not working. Let me try one other thing using different kind of quotes. No dice. When I do O star, that allows something to repeat 0 times, 1 times, 2 times, 3 times. The 0 times option, it means it can match anything because it creates the empty string. So this is actually the entire text, but wherever the O's appear, it it'll highlight them in red. Like there's an O. It's only matching the first one. Yeah, it's matching the shortest possible variation of this, which is always the empty string if it's not at the beginning. All right, but if we want, for example, words that start with one letter and end with a different letter and have anything in between, like words that start with the letter T and end with the letter E, or let's say T again, and then there's something in between them, anything in between. So dot star means any character any number of times, and then T again. So this is the sequence of letters that match that. But you'll notice that this includes some things I wasn't expecting, like this whole phrase, because it begins with a T and it ends with a T. The things in between it, though, include some spaces. So if I want to change that so it's only words, not whole phrases, I have to change my pattern. So can anyone see how this pattern could be changed to include only words and not phrases? The problem is that this middle part here, dot star, is matching anything, including things with spaces. So we want to allow characters to repeat, but we don't want to allow any of those characters to be spaces. So we can actually create a class of characters that's not space here. So now I have see this like bracket, caret, space, bracket, star. This means anything that's not space can come after the T, and that can repeat any number of times, and then after that there's another T. So now that pattern matches these words like tumult and that, a lot of that's. That's the most common one, right? Thought, that's a good one. Okay. I don't know why this double quote is being matched in this thing, but so it is. It's a good question, though. So we look at this output and we see that here we have a double quote and then THAT. Why is that included? Why is that included? Yes. Because the double quote is matching this first character, right? Because it's not A through Z or A through Z, and it's making it red. So whereas normally the thing that's before the letter is a space, when we make a space red, it doesn't show up as red. But here, this double quote character is showing up. I believe we can. Yeah. Anyway. Okay, we can also we can use or on longer patterns. So if there are two different patterns and you want either one of them to be matchable, you can put them in parentheses and put a pipe between them. So literally this or that we could make a pattern for. We can search that pattern here and see what happens. And by the way, this text file is on Canvas. You can download it and try it if you want to follow along. That didn't work. Sometimes grep doesn't really require some special modifications to get, requires a different variation of regular expressions, which is kind of annoying. Yeah, so or doesn't really work that way with grep. All right, so these patterns are useful for picking out like numbers and things like that, dates, email addresses. Those are things you might want to find in a document to do an analysis, because those things follow patterns. You know, so this is useful for picking out not really language level meaning, but picking out tokens of different types. Here's an example of a pattern. This *1 dot star t. Well, this matches 12.1. Yeah, different combinations of numbers and things that end with t. But you can imagine building out patterns like this to match different number formats and dates and whatnot. Yeah, just these other examples give some more practice with some of these symbols, like question mark here. If we want to look for the word cat, but we want to allow it to be plural, like cats, then the S at the end can be optional by putting a question mark after the S. And then we've also included both the upper and lowercase version of the beginning. And yeah, and those here, the plus after the 0 through 9 means that the number 0 through 0, the number 0 through the letters, characters in the range 0 through 9 can appear any number of times, but it has to be at least once. That's what the plus means. And then there can be one character in between them, and then there can be one letter character. So these things match here because you have a bunch of numbers, at least one number. And I'm not I guess I think I accidentally cut out the last thing that was last example was supposed to be here. But there doesn't have to be a letter at the end, so the second one, 23 period, matches. Yeah. And here I have a pattern to match either cat food or dog food, or also cat and dog, because this food part at the end is optional, but the food always has a space before it if it does appear. And cat or dog can be capital or lowercase. Yeah. All right, so if we wanted to find all the license plate numbers or license plates in a document, that's a pretty good use case for regular expressions because they have a certain format that's pretty easy to recognize, or telephone numbers, things like that. If we know that the license plates are between 6 and 8 characters and they sometimes have a space or a hyphen in between them in the middle, how can we write a regular expression for that? So that's a question for you to answer right now. So why don't you think about that for a second, and I will get this projector ready and we'll try some different options. Yeah, I guess it might be hard to answer that without having a reference of the different symbols that I've been talking about. But all right, so license plates. You want to match some letters, numbers or letters. Actually, I guess I can do this in the terminal, not necessarily on pen and paper. but 6 to 8 characters with a space or hyphen in the middle. So that means that at the beginning you have 3 to 4 characters, and then here you have a space or a hyphen or nothing, and then you have 3 to 4 characters, right? So you can translate this into a pattern by making a pattern for each of these 3 parts and sticking it together, right? So the 3 to 4 characters, by character we mean something that can appear in a license plate would be like a capital letter, but it could also be a number, right? Like 0 through 9. Those are all valid. And in the middle, and it can be 3 or 4 of them, so we can use this quantifier here. This is the minimum number, the maximum number, and this applies to the thing that was before, which is the set. The space hyphen or nothing here is optional, so we have the possibility of a space, which we can represent with by typing a space character here. And hyphen has special meaning inside of this, so we have to escape it with backslash. And it's optional, so we put question mark, and then we repeat this whole thing again for the second part. Right. Seem right? Yeah, so we just break the pattern, combine multiple patterns to match the different parts of the thing we want to match. And the only trickiest part of it, I guess, is that this hyphen normally has special meaning inside of square braces, so we have to escape it with a backslash. And that tells the regular expression parser that the thing coming afterwards doesn't have its normal meaning. It has this, just interpret it literally as a hyphen character. All right. Yeah, so special characters are often necessary when doing pattern matching. And so white space in text actually can have a variety of different representations if you're looking at the character level. So there can be tabs, there can be new lines, carriage returns, there can be spaces, there can be multiple spaces. And to represent tabs and new lines and carriage returns, so at the end of the line, basically the special character that causes the editor to start the next line is, it's either one character or 2 characters. It's either /n or /r/n. R means carriage return. Really, it mainly depends on whether you're on like Mac or Windows or Linux or whatever. But if you want to match any type of white space, you can create a set of different characters that represent white space like this. There's also a shortcut /s in regular expressions for any kind of space. And the reverse of space is /w, which represents a word character, which is kind of like the set of anything that's not a space character. Okay, so those are useful. All right, so I already did a little bit of a command line demo, but yeah, so maybe we'll just take a quick break and then move on to the next topic. Well, okay, before doing that, let's summarize what we've seen so far. So regular expressions are used for matching text, and you can use those in SQL queries, but also in other tools, like just plain command line tools and other programming languages that have libraries available for dealing with text. And there's some special characters that you need to be aware of that do different things, like matching sets of characters, ranges of characters, the reverse of sets, and also allowing repetitions. And this is a really quick reference of the most common features of regular expressions, but there are more of them. Okay. So let's just take a really quick break and Okay. So we've been talking about patterns, and patterns are useful for picking out like simple things out of text, or finding entries from among a list of texts that have certain characteristics. If those characteristics are pretty easy to define, or pick out numbers, pick out license plates, pick out telephone numbers, pick out email addresses, things like that. Those are all amenable to using patterns. But patterns alone don't really capture the deep meaning of language. Okay, so let's say you want to find in that Yelp database all the positive reviews, and also negative reviews. So looking at this particular review, it says, interesting food, great atmosphere, great service. I like this place because there's really isn't anything like this in Charlotte area. I will definitely be coming back. Oh, and milk bread. So is this a positive review? Yeah. Because we understand what the text is saying, right? You can't write a SQL query really to tell you that. That's positive, But can we maybe use regular expressions to determine that this is a positive review? Any ideas? I mean, could you try? If you were to try and that's all you had, how would you do it? Positive words, yeah. Great. So this particular review has the word great twice. Interesting. Definitely maybe is positive, maybe not. But yeah, the word great and interesting, maybe those are signifiers, like place markers or markers of positive reviews. So we can search for those positive words like good, great, love, excellent, best, happy. But that's not going to be perfect. Although we'll find that in reality there's no perfect solution. But still, it's a pretty coarse approach. So like if you have a review has both positive and negative words, like our waiter did a great job of ignoring our table, that's not a positive review, right? Has the word great in it. I mean, it also has the word ignoring, so maybe you can search for both, and then if both are there, you can cancel them out. But clearly, just looking for particular words and using patterns is brittle. It's not going to easily give us an answer to this problem we're trying to solve. So we need to use some kind of better analysis of the content of the utterance. So to start with, so most natural language processing tools, or many of them anyway, as a first step toward being a little bit more intelligent than just looking for words, they look at the frequency of words. So if we look at the text and we treat it as a bag of words, this is a technical term, bag of words, okay, meaning that the order of the words is not important. So it doesn't matter like what word is next to what. It just matters what words were used, how frequently were they used. If we translate a sentence into a bag of words or a document into a bag of words, the advantage is that it becomes easier to do a comparison. We lose information that the ordering gives us. We know the ordering in real language is important, but analysis becomes, some kinds of analyses are possible. So specifically, we can use a word frequency vector to represent a bag of words. So a word frequency vector is a vector that has a lot of dimensions. So one dimension for every word, every possible word. So like, let's say that your dictionary has all these words, like a, acha, and aardvark, all the way to zygote, zymergy, and zzz. There are 30,000 of those, let's say, or maybe 100,000. Then if you can translate a text into a vector like that by indicating a number in each dimension corresponding to the frequency of that word. So if you have a text that says, I like cats like that, that's 5 words, right? We can represent that as a vector with 30,000 dimensions by just taking, storing a number corresponding to the frequency of that word in the text. So there are only going to be 4 different dimensions that have a non-zero value, because there are only 4 words. There's I, there's like, there's cats, and there's that. Most of them appear once, like appears twice. So we have a 20% value, 0.2 for cats, I, and that. and we have a larger value, 0.4 or 40% for like, right? Because the word like appears twice. And this is a huge vector, lots of zeros, because most of the words like aardvark and zygote are not mentioned in this utterance, but a few words are, okay? So, and I just gave random examples of what these might be. That the 8,301st dimension represents the frequency of the word cats, and that's where we have a non-zero value, and so on, right? So each text, regardless of what it is, can be represented as a point in a space of extremely high dimension where there's one dimension for each word, and the value of the dimension is the frequency of that word. Okay, that makes sense. So why is this useful, and what does it give us? So to motivate that, we can actually look at. So here's one example where you can see that it's useful. You can compute word frequency vectors for not just little phrases, but big documents. So for example, you can take an entire Shakespeare play, and here are 4 of them, and compute the word frequency vector. Actually, these aren't frequencies, but counts. But it's kind of the same thing. The word count, you can divide it by the total number of words. And I'm only showing 4 dimensions. So these are 4 particular words out of, let's say, 30,000. But these are ones that maybe are illustrative. Okay, so the word battle is mentioned hardly at all in 2 of these, but it's mentioned several times in the Julius Caesar and Henry V play. The word good is mentioned kind of across all 4 plays, so maybe that word's not very informative in distinguishing the difference between these plays. The word fool is mentioned quite a few times in these first 2 plays, but hardly at all in the second 2. And the word wit also is mentioned quite a few times in the first 2, but not in the second 2. Right? So we can see that if you know anything about these plays, there's a difference between As You Like It, Twelfth Night on the one hand, and Julius Caesar and Henry V on the other hand. 2 of these are comedies. The other 2 are like history or tragedies. I mean, Julius Caesar is kind of a history, but it's considered anyway. It's kind of the same thing. It's these are both history or drama plays. So if you're writing a funny play, you might use the word fool and wit a lot. If you're writing about a lot of battles, then that's a different type of play, right? So the word battle shows up quite frequently. So the word frequency vectors would include lots of other entries, but I'm just focusing on 4 that are different, that have different types of values, or illustrative. The good has roughly the same values, but anyway. So depending on the task you have at hand, different dimensions of this word frequency vector are going to be important, but clearly you can make some use of this to do analysis. So if we take those word frequency vectors for these 4 documents, right, these 4 plays, and just focus on 2 different words. These are just 2 dimensions out of 30,000, okay? So battle is 1 dimension, fool is the other dimension. And if we look at those vectors just in those 2 dimensions, you see a big difference between 2 classes, the class of dramas and comedies, right? So dramas have a high frequency of battles and a low frequency of fool. Comedies have a high frequency of fool, low frequency of battle, right? Fair enough. And so therefore you can see that this is some motivation where word frequency vector can help to classify these 2 documents. I mean, we're only looking at 2 dimensions of the word frequency vector, so you have to somehow, you might need to ignore certain dimensions or figure out which dimensions are not providing a distinction. But this clearly can be useful if used well. But if we don't, I mean, this was like a carefully chosen example where we could have like guessed some of these words, or maybe we went through and looked for the ones. We knew ahead of time what the 2 classes were going to be, and maybe we looked for what words were popular in one and not in the other. But in general, if you don't know too much about your documents and you just want to see which ones are similar, which ones are dissimilar, you can take those word frequency vectors and compare them using the cosine similarity, which is to say just the angle between them. And in this case, if you're looking at just 2 dimensions, if we had, in reality, you're going to be working with very high dimensions, so it's hard to visualize what the angle between 2 vectors in a 30,000 dimensional space is. But this, you can visualize it in 2 or 3 dimensions, and the same concept applies. If the values tend to be the same for 2 vectors, then they'll tend to be pointing in the same direction. Especially since these are frequency vectors, the total length of the total, like if you add up all the dimensions, you get 1. So they're roughly the same magnitude. So the angle between them can be an important measure of how different they are, how alike they are, right? So these 2 similar ones, at least in these 2 dimensions, have a small angle between them, and these 2 have a high angle between them, right? And to calculate the cosine similarity, basically you just take the dot product, which is going to be greater if they're pointing in the same direction, and you can divide it by the magnitude squared. Or the product of the magnitudes of the 2 vectors. And this will be, so cosine similarity will be 1 if they're pointed in exactly the same direction, if they're identical, and it'll be 0 if they're completely orthogonal. And it can't be negative, for example, because these frequencies are always positive. So you won't have like a vector pointing in one direction and a vector pointing in the complete opposite direction. That would require negative values, which won't appear in a frequency calculation. Right. Okay. So those are word frequency vectors. So we want to, if we rewind back to the idea of finding positive reviews in a Yelp database, so we can use word frequency vectors to represent each review as a point or vector, depending on how you look at it, in some extremely high dimensional space. So here's a visualization of a bunch of points in 3D space, but in this case, we're not going to have 3 dimensions, but like more than 10,000 dimensions, 1 for each word. And what's that noise? So, we might assume that maybe the positive reviews are in one region of that space, and the negative reviews are in a different region of that space. That's kind of what we saw with if we knew what dimensions to look at, like that contrived example with Shakespeare had a clear clustering in that space of the 2 different classes. And in particular, if we have a few reviews that we know are positive, like we have some training data, to use machine learning parlance, then we can look for reviews that are close to those other positive reviews in this space, and those maybe will be positive too, right? Which is basically what supervised machine learning is at a very high level. But you have to, in a real machine learning system, you would kind of learn which dimensions are more important than others for solving a particular problem. Because again, not every word is going to be equally important for distinguishing comedies and dramas, for example, if that's what you're training on. So far we've had these word frequency vectors with like 10,000 or more dimensions. That's fine, but we don't really need that many dimensions, and it can be counterproductive to have so many dimensions. Because many words are similar, and you might want to capture the similarities in like classes of words, things like that. So I think probably many of you have seen principal component analysis. That basic idea of taking a high dimensional space and reducing it to fewer dimensions by looking for axes in the higher dimension that have the maximum variance. That can apply here. So you can take a 10,000 dimensional word frequency vector and all the documents in that space and figure out which ones have the most variation. So if every document, for example, has roughly 10% of the words are the word a or the, and that's the same across all documents, basically, that principal component analysis would throw that dimension out, essentially. And similarly, if the words good and great tend to appear with the same frequency in documents where they do appear, then you could potentially combine those into one dimension. A principal component analysis also would do that. Now, the downside of doing that is that you would end up with dimensions that are kind of difficult to interpret. I guess it'd be a linear combination of words, but they wouldn't correspond directly to individual words, so it'd be harder to say, oh, this is the thing that I can use to to do classifications, but it can give you better results and also reduce the size of the data in your analysis. In practice, these things called word embeddings are used to reduce the dimension of word frequency vectors. So instead of having one dimension for each word, you actually have a vector for each word. So you decide ahead of time how many dimensions you want to have in your word frequency space, or in your semantic space, let's say, your meaning space, and you use some kind of training set, like a huge language corpus. Like, for example, you might take all of Wikipedia, and you can use the co-occurrence of words. Like if certain words are usually near other words, and you can assume that maybe they have similar meaning, and that can tell you that like in general, when you see a certain word, like the word book, it tends to co-occur with other words, and therefore it should be represented by a vector that has components for those that's proportional to the frequency of those co-occurrences. That's used to take a document and translate it into a representation that has fewer dimensions than like one dimension for each word. I realize now I don't have, this is not a sufficient explanation to really convey the idea, but suffice it to say that word embeddings are a way to reduce the size of your word vector to represent a sequence of text in few dimensions. It's similar in concept to principal component analysis, except it's trained on a large language corpus, and you're assuming that the samples you're using are similar to the large corpus that you trained on. And this basically allows you to detect words that are similar to each other and to define words in terms of their closeness to other words in common occurrences. So. Yeah. All right. Did that? Yeah. So I'm not sure that how helpful that was, but at least is in spirit of data processing and data management information processing. If you want to deal with data, if you want to understand natural language, representing natural language as a bag of words and the frequency of those words, using the frequency of words in a utterance and the types of words that are present in a text to compare it to other ones, to allows you to help, is helpful for doing analyses. So word vectors are a way to translate text which has unclear meaning to a computer into a vector which can have clear meaning to a computer, although it doesn't necessarily translate into something that's useful for your domain. All right, so we also introduced regular expressions for matching patterns, and those are much more complex types of patterns than we could do with just the like having wildcards for individual letters. We could have repetitions of different numbers of times and sets of letters that are allowed or not allowed, which is quite useful. And yeah, so the examples I gave for doing natural language processing were review sentiment, like positive or negative reviews. You can also apply this, and we've also looked at document classification, like whether plays are comedies or dramas. The same concepts can apply very easily to like email spam detection. Emails, if you translate an email into a bag of words and look at the word frequency vector and compare that to other word frequency vectors of other emails, and you have those labeled as like spam or not spam, then somehow the closeness of those of a new word frequency vector to one that is labeled will help you determine what it is. Although to do that you have to write some code or use a machine learning system that handles these type of data. All right, so see you on Tuesday. We'll have a review lecture, and then the exam is on Thursday, and make sure that you are working on your project.